There we go. Okay. Right here I've got the equation y equals 2 to the power of x. Yes? Is that growth or decay? Based on the graph's increasing, and also based on the equation, this is the base, right? Base is bigger than 1, so it's growth. If I change the base to some kind of a fraction to 0.5, now the graph is decay. That's stuff we all talked about last time. That's nothing new. What if, well, consider something here that I hope you remember from a couple units ago. If I asked you to grab this, what would you be grabbing? A parabola. What if I asked you to grab this? It's still a parabola, isn't it? It just moves up 2 units, right? What if I put minus 2 right here? Moves down 2 units. What if I did this? Is that still a parabola?
Yeah.
That one moves to the left 2 units. The same type of things happen with exponentials, depending on where you put different things. For example, if I put a plus 5 or a plus 2 after the exponent, look what's happening to the graph. Now you can't see. Let me move that. There it is. So there's a plus. Can I get the 3? Oh, there we go. There's a plus 3. What did it do to the graph? Moved up 3 units. If I change that to a negative number, it's moving down. Exactly. That's a great question. Let me move it back to 0. There it is. Let me move that back to 2. So now this question. If you go from right to left, isn't this graph getting closer to 0?
Yeah.
It's because there's a plus 0 right out here, right? If I move that up to plus 1, now what is it getting closer to? Is it getting closer to 1?
Yeah.
Okay. So that number is pretty important. It just moves the graph up and down, and it also tells you where that graph has to approach. Now, inside the parenthesis here, if I put a number inside the parenthesis, like x plus 2 or x minus 5, what do you think that's going to do to the graph? Going to move it right or left? Come on now. So I've got x minus 2, or 2.1. What direction did you notice it moved the graph? It's to the right. Okay. If it's in with the exponent, it's moving the graph right or left. Okay. If it's plus a number like x plus 2, notice what happened to the graph? Move to the left. This is all stuff you know. We've done this with other functions. Now we just have to do this with exponentials. Now, oh come on. There we go. What if I put a number in front of 2, like 2 times 2 or something? That one. Where is it? There it is. So now it's 2 times 2 to the x. What happened to the graph? Did it move? It's getting steeper or flatter, I guess you could say, right? So that, oh, what if the number goes negative? Then it flips upside down. And you've seen that before. What if I put a negative sign in front of the x squared? What does that do to the graph? Doesn't it flip it upside down?
Yeah.
So the same thing happens here with our exponential. It could flip upside down if that number in front is negative. So I want you to go to your books on page 522. Sorry, 322. Okay. Go to page 322. You guys there? Look at the very bottom where it says problem 2 got it. You don't have to graph part A and part B. All you have to write in your notes is your description of the transformation. Like, is it moving up 10, or is it moving to the right 4? What's happening on those? The problem 2 got it, part A and part B. So look at part A, look at what it changes. It's y equals 4 to the x plus 2. So you've got to decide what that plus 2 does with the x. Does it move it up down, move left, right? You guys understand what I'm asking you to do?
Yeah.
And do the same thing on part B. Try to describe what changes are occurring in the graph. But you don't have to graph them.
Well, we're going to have to repeat that whole thing now. Moves to the left 2 units there, up 5. Dang it, we had that pause for like 10 minutes. That's going to be weird for whoever's watching this. All of a sudden, boom, there's the answers. And I'm just making it more awkward by talking about it. Sorry, whoever's listening to this. Am I wasting more of your time out there? Okay. Moving on. It's kind of weird. I'm talking to a future person who's going to listen to this.
I know, that's kind of weird.
That's weird. I'm on YouTube, so this is going out to the entire planet.
Okay. You guys with me? Going back to what, I don't know, was it Dallin I think was noticing this? Back on this, if you move the graph up or down, this number out here, like negative 2.6, isn't that where the graph kind of flattens out at negative 2.6? Or if you move it up to 3, doesn't the graph kind of flatten out at 3? Whether it's growth or decay, if it's decay, doesn't it kind of flatten out at 3? I want you to represent that spot where the graph flattens out with a horizontal line. And here's what I mean. So for this graph, oh, you gotta take it off that. What did we finally call that? Baby blue? Sky blue? Cotton candy? I have to see this on your test, you guys, to get full point. What does this do to the graph? Moves it. This one right here moves it up 2. So what I would want you to do, if this were a test, is go up 2 units and put a dotted line, a horizontal dotted line. That means your graph is not going to cross that line. It's going to approach that line and flatten out, whether it's growth or decay. You guys okay with that? This isn't actually part of the graph. It's just there to help you shape your graph and make it look better. There's a word for this. It's kind of a strange word. It's Latin. And you learn a little bit more about this if you're taking pre-calculus next year. But you might as well. We want to take a stab at that? Asymptote? Yeah. The P is solid, asymptote. What you really need to know for right now, all that means is it's some kind of an invisible barrier that the graph approaches and then kind of flattens out near the asymptote. For right now, that's all you need to know. So, first thing I would need you to identify is where the asymptote is. Second thing I would need you to clearly mark on your graph is the y-intercept. I have to see that that's correct. You can't just eyeball it and say, all right, the graph looks something like that. I need to see the y-intercept in the spot it needs to be in. Well, you guys know how to find a y-intercept. You let x equal 0. Now, 0 minus 1 is negative 1. 2 to the negative 1 is 0.5. Here it is 0.5. And then 0.5 plus 2 is 2.5. So the y-intercept is 2.5. Now, some of it, I showed you that just doing it in your head. I don't expect everybody to be able to do that. So on a calculator, you can just type in 2 to the negative 1, and then add 2 to that, and it gives you 2.5. No reason not to use your calculator if you're worried about doing that in your head. So, what's that? Well, yeah, because x is 0, and then 0 minus 1 is where the negative 1 came from. Third thing is you've got to decide what kind of exponential. Is it growth or is it decay? Which one's this one?
Growth.
This is the base. The base is bigger than 1, so that means it's growth. Why would you need to know that? Growth functions start here and increase. Decay functions start way up here and decrease. Once you've decided whether it's growth or decay, here's where I'm going to allow you just to kind of eyeball it. If you know it's growth, it's going to start along that horizontal line and increase like that. Okay? That's all I would need you to show. Yeah, I'm not too particular about that. Now, guess what would have changed if I put a minus sign in front of that? Really, a minus sign in front means minus 1 times 2 to the x. So the base is still 2, so it's still technically growth, but what does that minus sign do? It would flip it upside down, so the graph would look like that in that case. But it's still considered a growth function, because the base would be bigger than 1. Right. So if there's a negative sign in front, it just flips the graph upside down. You got that? So I want you to look at the top of page 323 now. Page 323 right at the top, you see those two graphs? Do those two graphs. Not in your book, not in your paper.
Top page 323, I want you to draw those two graphs.
Yep, practice A, question 3 and 4. Don't forget to remind me to unpause this.
Yes. What, the horizontal asymptote? Which one are you talking about? So it is the graph moves to the right, yeah. When you plug a 0 in for x and you find the y-intercept, that's your y-intercept. That's already been moved 1 to the right. It's on the y-axis still. It's 0, 5.5.
So your line is just
You're going to do number 3. Yeah. Yours was right.
It was.
It is now. Wait a minute.
We are recording. All right, Caitlin, go ahead. Hey, she got it right. Watch it. Now just draw the graph. It's harder than it looks, isn't it? I went through years of training on this board. Good. Up 4 units. And the y-intercept is 5.5. Is that what you got? Good. And it's a growth function. Good. That'll do.
Thank you. Questions? Yeah. All right, guys, check it out. Here's 4. What does the minus 5 do? Come on now. Moves it down 5 units. So that's where our horizontal line is going to be. Man, this was not good. Okay. What'd you guys get for the y-intercept on this one? When I heard it now, say it with pride. On number 4.
Negative 5.67.
You're hearing a couple different numbers.
It's negative 11. You plug it in, you plug in 0. It's a negative 11. Sorry, guys. You lose. It's negative 11.
She sounds pretty confident.
Is it? Is it negative?
Who's going to back her up? Who got negative 11? They got 7 of you. What the rest of you get? Nothing? It is negative 11. It is negative 11. Hey guys, check it out. You plug in a 0 for x. What's 0 plus 1? Hey, come on. Easy math here. 3 to the first power. 3 times negative 2. Negative 6 minus 5 is negative 11.
Oh.
So you got to go all the way down to negative 11. Hey, I got a question for you. Normally, exponential graphs are above that horizontal line here. Why is this one below it?
Because it's negative 2.
The negative 2 right there. So, your graph ought to look something like that. Exactly. Ooh, nice. Nice. Yeah.
How did you know it's this way and that way?
And not this way?
Yeah.
Because that's a good question. If the minus sign weren't there, right, then it would be a growth function that looked like that. So the minus sign just makes it a reflection. It flips upside down. Does that answer your question? This is still growth. Whew. Okay, one more thing we got to do. This got to happen real quick. Real quick. If I told you guys to tell me what this symbol meant, what does it equal? It's 3.14. Did we just talk about this? I made a big deal about it? Well, that's just a symbol that represents a number. You guys okay with that?
Yep.
This is not a variable. This is a symbol that represents a number. There are other symbols in mathematics that represent numbers, and they're not variables. One of them is called the natural number. Okay. This is our next topic. We only have 6 minutes, so you guys got to write quick. There is a number in mathematics called the natural number. And they've chosen to give it the symbol E. So now E is a number, it's not a letter anymore. In this section of your homework, when you see that E symbol, it's not a variable that you plug things into. E represents approximately 2.71. It's kind of a confusing process to show you where it came from. So I'm going to skip that for right now. For right now, just got to believe me. Actually, do this. Get your calculator on. Come on. Hey, John. Get your calculator on. Hit the second button. And then in the left column, all the way down to where it says LN. Hit second and then LN. Do you see how it gives you an E? It's on the left column, third button up. Now type to the first power. I want you to go E to the first power. And hit enter. You do second and then the natural log button. And what is it? It's about 2.7, I guess 2.72 if we're rounding, but that's the value of E. Okay? It's not just that somebody said, well, let's let E equal 2.718. There's a process that a mathematician went through to come up with this value. It's just kind of a complicated one. I don't have time to show you. So for right now, when I ask you what E is, you say it's 2.71. And it's called the natural number. The reason they chose E as the letter is the mathematician that developed the process. His name started with an E. Anyway, the reason it's called the natural number is it's used to describe a lot of phenomenon in nature, like population growth, radioactive decay, money growing in bank accounts. You can use E for all sorts of things. Okay? What we're going to use it for is this. Oh, did the bell ring? Is that why we're putting stuff away? Oh, no, it didn't ring. We're still going, you guys. Keep your stuff out. When the bell rings, you can put it away. We're still taking notes. Because I have to erase the circle around it. It's going to be on your assignment, you guys. If you don't want to listen to it now, you can try to figure it out on your own. But you don't put stuff away till the bell rings. While I'm still talking and taking notes, you still take notes. Okay? The P right here is called the principal. That means the principal investment. If you're talking in money, in terms of money, the principal investment is what you start with. Or it's the principal amount that you borrow if we're talking about a loan. Okay. What do you think R stands for? Rate. And then T stands for? Time. So it's pretty easy. You guys are going to have this memorized on the test. You might want to put a box or something around that. I'm not going to tell you what the formula is. You've got to have it memorized. Most students just remember the phrase PERT. PERT. And you use it for continuously compounding interest. Now listen. Didn't we start the day with an interest problem? That's called simple interest. If it's only accruing one time per year, that's called simple interest. And you don't use this formula. You guys follow? If you see the phrase compounding continuously somewhere in the problem, this is the formula you use. And it's really easy to use. It takes like 5 seconds. Check it out. I don't know what you guys' hurry is. Do you have some special date or something after this? Yes. Okay. Lunch isn't going anywhere, you guys. Write the problem down. If you'd like, I can close the door and I'll wait till I hate to do that, but I don't have to let you go when the bell rings. So if this becomes a big problem, I might have to start doing that. But you don't put stuff away until the bell rings. Well, I'll tell you that in just a second. Suppose you invest $5,000 into an account yielding 4% interest compounded continuously. What's the model? First of all, what's the model? Ryan King. What's P going to be in this case? 5,000. What's R? Hold on. What's R? So how do you write that? Okay, so here's the mile, 5,000 e to the 0.04 times t. Right? So, if I ask how much after 5 years,
So you plug in 5.
so go ahead and do it. You got to practice this. It's a lot easier sometimes said than done.
At this time, I need the following students to the front office: Skylar Schmidt, Marley Johnson, Sam Bridge, and Cynthia Gardner. To the front office, please.
How much after 5 years? So yes, this is what it looks like on your calculator. 5,000. Where's the E button? Second, ln, and then 0.04 times 5.
6,000.
How long does that take? A couple seconds. These problems are really easy. What's the key that made you know you're going to use E? Continuously compounding. Okay? Any questions on that?
No.
Okay. Now you may go and run to the lunchroom. Apparently you're so hungry to get there.
I had to take that test. I thought I did it, but it ended up having to in school. And so, can you leave that with a teacher so I can take it?
Today?
Yes, I haven't taken it yet.
Which